a quotient here, if there's like a division, the sort of key as far as what rule we're going to use is what the denominator looks like. So I'm actually just going to over here write our 3 rules of integration. So u to the n du is u to the n plus 1. That doesn't look like an exponent. Let me stop for a second. Okay. So these are 3 integration rules, and all of our integrals are really based on these 3, even if some of them get a little more complex. They're all based on this. And so if we have a quotient inside of the integral, it's either going to be a natural log situation because we have a denominator there, or it could be a power rule.
That's what I was looking for, the power rule. I was like, I know it was one of the rules.
So on this one, this is a u substitution kind of problem that I just wrote.
Okay. So the u equals the x squared plus 1.
Right, exactly. And so we don't even need to think about which integral rule will actually be needed until we kind of identify our u and get it into a simpler situation. So that if u is x squared plus 1, then what is du going to be?
X over dx? No.
So don't look at the original.
Oh, yes, 2x.
2x dx.
There we go.
Yeah, so du always comes from the u, not from the original integral. That will mess you up.
Okay.
But then once we have du, we do need to look back at the original and think about what we have there that we
just have the x, so then we need to move the 2.
Right, exactly. So we would have 1/2 du equals x dx.
Okay.
So then we have all of our parts in the original integral that can be replaced with stuff in terms of u.
So the bottom will be u. And the top will be 1/2 du or 2 du.
So it's not 2, because if that 1/2 is going to be on top, it wouldn't flip over. So we could technically write it like that, but I don't recommend writing it like that. So the u can really just be thought of as 1 over u, because the u is just in the denominator, and that x that was up top is being swept away. So there's really just a 1 left over.
Okay.
And the x dx is being replaced with 1/2 du. Which I would recommend bringing that 1/2 out so it's just out of the way, and we could do that right off the bat.
Okay, then it's natural log u and absolute value du.
Yes. Or not du anymore.
Dx. Oh, plus c. That's right.
So once we do the integral, that du or dx or whatever it is goes away.
Okay.
And we have one last step here.
I'm not seeing it.
So our original problem was,
Oh, oh, so 1/2, is it 1/2 over? Two U? 1/2U?
that would be going backwards.
Oh,
So we're done with the integration. The integral step was to change the 1/u to ln absolute value of u plus c. Our original problem was x over x squared plus 1 dx. But our answer right now is in terms of u.
oh, okay, so 1/2 natural log absolute value of x squared plus 1 plus
Okay.
c.
Yes, exactly.
That'll take me a minute. It's been a while since we've done those. Okay,
So this is an example of a substitution problem. Where we have to get everything in terms of u first, and then integrate and go back to our original. I want to address one thing, because I don't know if this completely addressed the initial question. So I want to do just a comparison of two simpler integrals to see the difference between a 1/u situation and a u to the n situation.
okay,
So, for example, if we have an integral of 1 over x dx and an integral of 1 over x. Oh, that's actually not going to work. Yes, it is. Yeah, that's fine. Okay. So these two look awfully similar, and so it looks like maybe they would use the same rule, but they don't.
so that one's the natural log of x plus c
Right, exactly.
in absolute value.
Don't know how to write a plus sign. There we go.
It's early-ish. And then the other one we use substitution, right?
You actually don't need substitution in this case, because there's no interior and its derivative here.
Oh,
How can we rewrite 1 over x squared so that it fits one of our rules?
1 plus x to the negative 1/2. Sorry,
Is it just x to the negative
2.
1?
So when we do the integral, a -1 will come out. But here, I'm just looking at rewriting it. So it is x to the -2. So
Okay.
it's the fact that we can rewrite 1 over x squared as x to the -2 that makes it this first rule, where we have just our something raised to a power.
Okay, so then it becomes x to the 1 over 1 dx.
X to the, what will be our new power?
-1
-1, yeah.
over -1 plus c.
And that you could either write -x to the -1 or -1 over x.
Okay,
So when we have a quotient in our integrands like this, if the denominator is just one thing and doesn't have an exponent on it, then that would be a natural log, because our natural log is always just 1 over the thing, whether it's a u or an x or a t or whatever it happens to be. Whereas if it's 1 over x or whatever to a power, then we can change it to the power rule.
Okay. Oh, I was talking about square root with a negative half.
Yes. Which might come up.
Yes, I'm sure. And we'll be able to use Desmos as well.
Yes, yeah.
Is there a way to check that your integral is correct? Because there's been a couple of times when I'm doing them in Desmos and on my calculator, I get 2 different numbers because I'm double checking what I'm doing. And so then I'm trying to figure out why I'm getting 2 different numbers. Usually it's because of placement of brackets.
There's really not a way to check to see if your answer is right.
Okay.
In that kind of situation, a lot of times if it's wrong, it seems wrong. Like if you get a negative when we're trying to find an area, that would be an issue. If you get a negative when we're finding like consumer surplus, or if it seems way too small or way too big. But there's really not a way to like go back and check.
Okay.
And I do want to highlight, since we were talking about Desmos, so there's a handful of indefinite integrals, which will have the plus c. So for example, number 8 says find the following definite integral by hand. So that means that you will do this integration by hand, not using Desmos or a calculator. This one also says by hand. But then once we get to the like chapter 6 things where we want to find the area between curves, I want to see your work on how you set up the integral, but then you can use a calculator or Desmos to calculate the integral. Don't spend a bunch of time trying to do this by hand. It is possible, but it's not something that we have gone over in this class. And so on your own time, it can be a fun thing to do. But during the test, please realize that you can use a calculator or Desmos to get that integral. And same with all the areas, the Gini index, consumer surplus. Everything we did in chapter 6, you can use a calculator or Desmos to actually find the integral, but you need to know how to set it up. So I want to see the like integral written out on your paper, but then you can do.
So quick question on like number 13, when you put in the equation into Desmos, and to get the line, you just put x equals, and then what, like for instance, that 160, and that'll give you the b for the integral?
You would have to do y equals.
Y equals, okay. Oh, that's right, okay.
Yeah, so
and it's always the positive number?
Yes, yeah.
Okay.
So if there might be some where the like price supply equation is a parabola, and so maybe it'll cross twice in the grand scheme of things, but we only care about positive numbers of units and positive dollars. So
okay. And labeling those is also key. Making sure that you're putting dollar signs where
yes.
dollar signs need to be put. Okay.
Yeah, units are important.
think that's all the questions I have. Thank you.
Yeah. Anything else? All right, so all of that stuff is in the Thursday test 4 heading in the module. So I put up the chapter 5 and 6 review sheet, that practice test, and the answers to the practice test so you can check. And then the test itself will be on Thursday at 11:30. So, great. So let's continue in chapter 7. We just barely started chapter 7 on last Thursday. So I just brought the first page of what we did on Thursday, or the last page of what we did on Thursday, to today's notes, just to refresh what we were talking about. So in chapter 7, we're talking about functions in several variables, doing derivatives and optimization and those kinds of things that we've done in one variable in more than one variable. So there are a couple ways to think of several variable functions. One of them is to think of it in dimensions. So usually when we just have y and x, that's just 2 dimensions, a flat plane. As soon as we bring that z-axis, now we have 3 dimensions. And so sometimes it can feel weird to think of, well, if we add another variable, now we're going to have 4 dimensions. And what does that look like? We could have 20 dimensions. We really don't know what that looks like, but that's okay. We can think in math in multi-dimensional space just from understanding how to do things with more than one variable. But we're not even necessarily going to be talking about space very much here. We will. But really what we're doing, and this was the example we ended with on Thursday, is that a way that multivariable stuff comes in that has nothing to do with like spatial dimensions is that if we just have lots of variables in a situation. So this was our example from Thursday where this kayak company was starting out producing just one kayak and they had this cost equation. But most companies are not going to produce one thing that's exactly the same. So this company decided to start producing another kayak. And so we have added one more variable. So we have x and y. If they decided to start producing another kayak, then we could add another variable, a z. And so we can have as many variables as we need for whatever situation it is. And there are plenty of situations in math when we need hundreds of variables or thousands. Those kinds of things, calculations are done in computers, but it's people, mathematicians, who are telling the computers what to do. And it all comes down to these things that we're going to talk about in this chapter of how we can extend our understanding of the calculus we've done in the first portion of this class to multiple variables. And I won't go nearly as in depth. We only have a couple of weeks in class left, but still. So this is the last thing we did on Thursday. So we have this cost function that takes into account the standard kayaks x and the elite kayaks y. And now we have this new cost function. And we saw that we can use this notation as well. If we want to know the cost of producing 15 standard and 10 elite kayaks, we can just plug those into our function, just like usual. So we're going to continue with this kayak problem for a little bit. And so all of this stuff that we've seen a lot in this class, the revenue, cost, price demand equations, can be extended to multiple variables as well. So suppose the kayak manufacturer from the previous example had determined the price demand equation for the two types of kayaks are P equals 200 minus 3x plus y, Q equals that, where P is the price of the standard kayak and Q is the price of the elite kayak. So we have these two price demand equations, one for each of these kinds of kayaks. And we want to know the weekly revenue function. So just as a reminder, in one dimension, we've done this a lot in this class, revenue is the number of items we're producing times the price that we're selling them at, or the number of items we sell times the price that we're selling them at. So if we are finding the revenue function for two things, we can think of it as the revenue we're getting from the standard kayak plus the revenue we're getting from the elite kayak. So we have two sources of revenue now. So the standard kayak, we're producing X of those, and they are selling at P dollars. And our elite kayaks, we are selling Y of those, and they are Q dollars each. So this is what we're told P and Q represent. P is the price of the standard and Q is the price of the elite. So this is sort of the basic structure of our revenue function, but of course we want it in terms of just X and Y. So the revenue from the standard kayak would be X times what P is in terms of XY. So that would be 200 minus 3X plus Y. And then the revenue from the elite kayak would be Y times the price of each of those, which would be 400 plus X minus 13Y. So our revenue function works exactly the same way as the revenue function in one variable. We just have to take into account that we're getting revenue for more than one thing now. So we have to add up all of those things. Let me move that for a second. And this technically is the revenue function, but let's just multiply it out so we have it ready for the next step. So we have,
is that supposed to be a plus before the XY on the second half?
yes, thank you.
You're welcome.
So we have, oh, that's good because that would have, anyway. So we have only two like terms here to combine the XY. So I just reordered the terms a little bit, which is not required. You don't have to, but this is, there's a couple standard ways, but I think this is the most standard, where our two variables are sort of going the opposite direction, where we're starting the highest power of x and then that one is decreasing, and the y is starting with the lowest power of y and then increasing. So it's not necessary to put the terms in this order, but that's kind of the standard order. So that's our revenue function. Oops. And part B. So this was the cost function from the previous page. And we want to know the weekly profit function. How do we find profit?
Revenue minus expenditures.
Exactly. So whether we're in one variable or 50 variables, that profit will just be the revenue minus the cost or expenditures. And so we now have to multiply or subtract all of those. And I am just going to put the minus cost down here. So our profit turns out to be oops, that should be 380.
Minus 800.
Oh, thank you. It's feeling like I missed something there. I couldn't quite find it though. Okay, so we have our profit. So these functions can get long since we have so many more like possible combinations of variables. We have fewer like terms to combine. But the basics are the same as we've been using this whole time, which is why I'm going through this kind of quickly. Because really the important parts here are profit is still revenue minus cost, no matter how many variables we have. And our revenue still comes from multiplying the number of units we're selling times the price each of those are selling at. We just have to consider if we're selling more than one thing, we're getting revenue from each of those different things.
I think I missed it somewhere. How do we know which one is X and which one's Y aligning with P and Q?
So the X and Y were defined on the previous example from Thursday. So that was X is the number of standard kayaks and Y is the number of elite kayaks. But then in the revenue example, it said below those two P and Q, P is the price of the standard kayak and Q is the price of the elite kayak. So we have to be told from the equations themselves, there's no way to tell, but we will have that as part of the problem.
So if Q is elite kayaks, then why does it even have an X in it?
Yeah, good question. So the Q is, the Q equals 400 plus X minus 13Y is saying that the price of the elite kayak depends on both the X and the Y. So all of this is how much people are going to be willing to pay based on all sorts of factors, our price demand equation. So it makes sense actually that the price of the elite kayak would depend on both, because the number of, it's going to get kind of inception-y, the number of standard kayaks we produce has an effect on the price of the standard kayak. So if we think about, like, as a consumer, if the elite kayak is like $500 and the standard kayak is $450, at that point, if I'm willing to spend $400 or $500 on a kayak, I'm probably not, I would probably be maybe okay with spending $50 more on the elite kayak. So that might be an okay price for me to pay. But if the difference is like the standard is 100 and the elite is 500, unless I'm like a super pro kayaker, I'm probably not willing to spend $400 extra for the elite. So the price of the two kinds of kayaks are related, which makes the number of them that we're producing related also. So all of that is sort of intertwined.
I see.
Yeah. And all of that, the price and price demand equations are all about like market research and what consumers are going to pay and all of those things. So making those equations are like a whole job in itself. So we're just using them, but yeah, that's a good question. Okay, so
Up to the first half of the problem, so I could get a screenshot of it.
yes,
Last week.
Last week, yes. And this, there we go. So 7.1, what we have talked about so far, is just sort of the like basics of translating what we have done with functions into multivariable functions, but we haven't actually done any calculus on any of these yet. So that is our next section. Am I good to change the page now?
Yep, good to go. Thank you.
Okay, no problem. Okay, so we're going to continue with this kayak example. So section 7.2 is called partial derivatives, and we'll talk about what that is in just a little bit. But so we're going to talk about this kayak again. This little part is just sort of a review of chapter 2 really, or chapter 3. So when the kayak manufacturer from the previous section was only producing one kind of kayak, their cost equation was C of X equals 600 plus 90X. So that's before they started making this other kind of kayak. So their marginal cost equation was C prime equals 90. So nothing crazy going on there. We have this marginal cost of the cost equation in just one variable. So our question that we're going to answer in this section is, what would be the marginal cost equation when they started producing two kinds of kayaks? So this was our cost equation for the two kinds of kayaks. 800 plus 90x plus 120y.
Multiply it times 2 to get 2?
Nope. So let's first start by remembering what marginal cost is. So marginal cost in our C prime of X equals 90, that is saying that it would cost $90 to make one more kayak. And that 90 comes from the number in front of X. So every time we make another kayak, every time we increase X by 1, we're spending $90 more for cost. So marginal cost is conceptually the additional cost for making one more unit of something. The thing here, though, is that we have two different things that cost two different amounts to make. So we actually need to think of these separately. So we haven't learned how to do these derivatives just yet, but I want us to just think about this in terms of this cost equation we have. So I'm just going to write these two questions. So we want to know the marginal cost of one more standard kayak and the marginal cost of one more elite kayak. Which is our y. Whoops, sorry. So if this is our cost equation, if we make one more standard kayak, which really just means we're increasing x by 1, how much would that increase the total cost?
By 90.
Exactly. And then how, if we were to make one more elite kayak, how much would that increase the total cost?
120.
Exactly. So in this equation, we're able to see that every additional x is going to increase our total cost by 90, since the 90 is being multiplied by x. And every additional y will increase the total cost by 120. Not all of our problems we'll be able to just look at and see them this way. We will actually have ways to find the derivative. But the sort of key here is that when we're looking at the marginal cost for one variable, the other one doesn't actually matter at all. We're just looking at what the increase is when we are focusing on just a standard kayak, increasing the standard kayaks. If we are looking at elite kayaks, the other kind of kayak doesn't matter at all. So when we do derivatives in multiple variables, we have to focus on which variable we're talking about. There is no general derivative when we have multiple variables. We have to focus in on whatever variable we care about at that time. And that is where partial derivatives come in. So partial derivatives are for multivariable functions. I'm going to make that smaller so I can keep it in there. So for partial derivatives, we're going to do the same type of thing conceptually, where we are looking at the derivative just for one variable and everything else doesn't really matter. Everything we already know about derivatives is still going to apply. There's just something we have to sort of shift our brains for a little bit. So this is the definition of partial derivatives. I'm just going to leave that up for a little bit, the verbal definition at least.
Does the partial derivative always come from the cost function?
No, it can come from any function.
Okay.
Okay, so for a function of two or more variables, a partial derivative is found by taking the derivative of one variable while treating the other variables like constants. So constants, we see constants all the time. They can be, usually they're numbers like 2. They can be multiplied to the variable we're looking at. They can be added, whatever. So the weird thing about partial derivatives is that our other variables, we're just going to pretend are constants when we're doing these derivatives. So here is, oh, actually, before we do an example, there are a handful of notations for partial derivatives. So z equals f of xy is our function in terms, yeah, it's not my fault. So z equals f of xy is our function in two variables, so in x and y. So we have that third z axis. And so we have 3 ways of expressing, really it's 2 ways of expressing each of the partial derivatives in terms of x and y. So if we are doing the partial derivative with respect to x, there are 2 ways we can write that. This is still read dz dx. So it's still read the same way we would read a regular derivative with a dy dx or something like that. But we have to use this weird looking z, or weird looking d, excuse me, to show that this is a partial derivative rather than a regular derivative. And really, we can know it's going to be a partial derivative if we have a multivariable function. But that is the way we express this is a partial derivative. We can also put it on the function itself. So this little x, this subscript x means we're doing the partial derivative with respect to x. And really, those last 2 are the same.
What's the apostrophe on the dx?
Oh, that's a comma.
Oh. Oh.
No, thank you for pointing that out, because when I look at it, that didn't look like that to me, but I can see how that is confusing. So I'm just gonna separate those. And there is really one more way. We can do that dx in the f notation too. So we could do df dx as well, and that would be fine, or df dy. So all of these mean the same thing, at least the ones on top and the ones on the bottom mean the same. So with respect to x, we have multiple ways of writing it, and with respect to y, we have the same ways.
What's the most common way that they use? Or is it just scattered?
So this way with the d, the weird d, is most common overall in math. But these are also common. I think our book uses these F1s a lot in the next couple sections we'll be doing. So you'll see both of them. It's sort of like, it's like the prime. This is like our analog to prime notation. We just can't use the prime now because we have to specify what variable we're looking at. So let's do this now that we know what all of these things mean. So I'm going to start by just scooting this up. Okay. So I'll give you a minute to get this function down before we get started. Okay, so part A, we are looking for dz dx with this weird d. So everything we know about derivatives still applies here. So this is a polynomial, just a bunch of terms added together with their exponents. So this is just going to be a power rule problem. The tricky thing is to remember that since we are focusing on x here, y is nothing. Y might as well just be a 1 or a 2 or something. It's still there, it still exists, but it is acting just like a regular constant number. So when we go through our derivative, so this first term is just 3x squared. Nothing weird is going to happen here. We take the derivative of that just like we normally would. So we get 6x. So that was the derivative with respect to x for that term. This next term, two x cubed y.
Would that also be 6x?
6x
Squared, right?
squared, yes, exactly. But there's still a little bit left on this term.
1.
Not quite.
Just y?
Just y, yes. So
I
that
thought since they turned to constants, so that rule does not apply when there's an x and y in the same section.
So it's still applying. So think of like this 2 up here, out here. That 2 is a constant that's being multiplied to x cubed. And when we do the derivative, that 2 is still there. It just happened to multiply with the 3 that came down. So the 2 was just hanging out, being there, still multiplying with whatever we started with. The y is doing the exact same thing. It just doesn't have anything to multiply with. It was there in our original term, and it's still just there. So when we're multiplying by a constant, that constant doesn't go anywhere. It can multiply with other stuff if other stuff happens to come to it, but otherwise it's just staying there. Same thing happened with this 3 in the previous term. That 3 was there, and it is still there. It just happened to get multiplied with the 2 that came down. So the y is also just hanging up. we look at the rest of the terms, we are doing the derivative with respect to x right now. There is no x here. Got two words, no x there or here. So what would be the derivative of minus 4y if there's no x in it in this case?
It's -4.
That would be the derivative with respect to y.
It's 0.
Oh.
0, exactly. So since there's no x in either of these terms, so the derivative is 0. For just those terms where there is no x. So this is the situation where the y is still like a constant here, but it's not multiplying with anything. It's a constant added to the end. And a constant added to the end always goes away when we do a derivative. So our final answer is this whole thing. So the only derivative rule we used here was the power rule. That's one that you'll remember forever from now on, probably, because we've used it so much. It's this turning our brain, like we have to sort of turn a switch off to stop thinking of that y as a variable and just focus on the x when we're doing this. So anything that's not an x gets treated like a number. So let's do another one. Oops. Ooh. Okay. So now, same thing, but we're doing dz dy. So I'm just going to rewrite to z. I'm going to leave off the f of x, y part here because we don't really need it.
So on this one, would the middle term still be the -6x squared y, since it still has a y in it?
No. So two reasons. One is that the power of 3 is only on the x. So this time that power of 3 is not going to multiply because the x is not what we're doing the derivative of yet, or this time. So the answer we got for part A is completely not, not here anymore. Sometimes we get similar elements, but it's not necessarily the case. So let's start with the first term.
0.
0, exactly. Since there's no y here, that is going to go away completely. So our second term.
-2x to the 3, 1.
We don't need the 1.
Okay.
But
So
yes,
then we don't include it.
right, exactly. So this one will just
Okay.
be minus 2x cubed. So here we need to remember to focus on the variable we're looking at. So this is just a y. So when we have, we're doing the derivative of, or when our variable is just multiplied to something and it doesn't have a power, our variable just goes away and the something is left over.
-4.
-4, exactly.
And then 0.
Right, exactly. So that's it for this one. So in this case, neither of those y's had an exponent. So we just took their coefficient. So in this case, the coefficient of -2x cubed y is the -2x cubed. That whole thing is being multiplied to the y. And then the -4y is just like usual. It turns into -4. So it might help sometimes for something like this -2x cubed y to, for a moment, just pretend like the x cubed isn't there and just think, if it were -2y, what would this be? And we know that then the y would go away and we would be left with just the -2. But the x cubed is part of that, so it is still there. It just can feel a little confusing at first.
Now, if that 2 wasn't there, then it would just be x cubed.
Right, exactly.
Okay.
So that trick might not be as helpful in that case, but yes.
Okay.
We're going to do a few more examples, but are there any questions at this point? Okay, let's just look at one more notation and one thing that we can do with these. Oops, before we move on to a new function. So here we have a different notation. So we have f sub y, so that's going to be the partial derivative of f with respect to y of 1/4. I'm going to scroll up for just a moment so we can remember how these things are related. So f sub y of xy is the same thing as dz dy, the derivative with respect to y. So we already actually found dz dy in part B. So that means we also know that f sub y of xy, without plugging anything in just yet, is the same thing as we found in the previous step.
So then we plug 1 for x and 4 for y.
Exactly, yes.
But if there is no y that's on there, or is that an imaginary y?
Yeah, if there's no y available, we don't need to plug it in.
Okay.
And that does happen sometimes, so that'll come up. And so now,
-12.
No.
Nope, sorry. I did that 2 cubed.
Yeah, so just the one is cubed, so really we have -2, -4.
-6.
Yeah, exactly.
This will be on the final exam, but won't be on the next exam, right? Or, yeah. Okay.
So let's do one more. I'm going to move this B out of the way for a second. So we don't have a z in this case, but we just have f of xy equals x to the 6th plus 6x to the 9th, y to the 6th. I'm just going to rewrite the function again.
Six x to the 5th plus 54x to the 8th, y to the 6th.
Right, exactly. So our first term is just x to the 6th, so the 6 comes down, power rule. Our next term, we do the power rule on the x specifically. So the 9 and 6 multiply to be 54. The power of the x drops by 1. And that y to the 6th is still there because it's just a constant hanging out, multiplying with whatever's next to it. So I am going to put a link in the chat. To a problem, and you'll see it's this same function that we're seeing here, and there's two parts. One part is the derivative with respect to x, which is this, so you can just type in what we got here. And then also find this one. So try the partial derivative with respect to y on your own and put your answer in that box on the link.
It's not letting me type into that box.
The only suggestion I have is to try refreshing it. But if that doesn't work, let me know.
You type on the left side, not the right side.
Yeah, it's still not letting me. Having a moment today.
Well, if it's not working, you can just chat it to me.
Chat it. Okay. This is
Hey, Madeline, I'm sorry. I don't know if my question came through or not. My internet went off as soon as I was asking it.
I did not get a question from you.
Okay, it wasn't important at all. I was just wondering why they write the D's the way they do for these, because I write my A's the same way.
Oh, I mean, I don't know why it is that D specifically, but it is to differentiate between a regular integral and or derivative, excuse me, regular derivative and a partial derivative. So
Makes
like
sense.
dz dx like this, it would be for just a one variable function where it's some z equals something in terms of x, whereas dz dx like this is a partial derivative.
Okay.
So they're read exactly the same. So if we're speaking, we would have to like say which one we're talking about, but in writing, this is regular and this is partial.
All right. I was just wondering.
Yeah, it is. To me, those weird looking D's look totally normal because I have been doing this for a long time. But when we first see them, I know that it looks pretty weird.
Right. Yeah, it caught me off guard when I wrote it.
Yeah.
I was like, that looks like a big A. I read my lowercase a's like.
How do you type that on the keyboard?
Good question. It's in the equation editor, which is how I did it. I don't know if there's a way to do it in like a regular keyboard. It has to be something that's specifically for math. And I actually can't even remember where I found it.
Is it the second one? No.
So if we're on the equation editor, oh yeah, that is it. You're right. And in a fraction, it's so common fractions that would be dy dx.
Okay.
But yeah, you're right.
Okay.
It is that little, there's a little d there. Oops. Okay, I'm going to see how this is going. Okay, so I'm going to give it a little longer if you haven't put anything in yet. Do that.
And you just wanted Y, right?
Yes.
Okay.
Or since you're just chatting to me, that's it. All right, let's look at this together. So I'm going to write our function again. So we have f of xy equals x to the 6th plus 6x to the 9th, y to the 6th. So in this case, we're switching notations here. If we're doing just the derivative with respect to y, this first term, x to the 6th, is just a constant. That might as well be a 5. It has nothing to do with y, so that one goes away completely and we don't use it. The next term, 6, oh, did I? Yep, I wrote a 9 instead of 6. Okay, so our next term is 6x to the 9th, y to the 6th. So I noticed that some of you, and this is fine, to start off going, okay, we have 6 x to the 9th, and those are going to stay there because they're just a coefficient of y to the 6th. So those are just going to remain there. And then we do the power rule on y to the 6th, which would give us 6y to the 5th. And so that's totally fine to write it this way as a step. We do need to simplify this a little bit, but this, I think, can be helpful. So the 6x to the 9th is just a coefficient that's multiplied to what we really care about, which is the y to the 6th. So y to the 6th, we do just the power rule on that to get 6y to the 5th. We should finish this off by multiplying those 6's though. So power rule is the only rule we have used so far. But it's really, it takes practice to get used to ignoring one of the variables and treating it like a constant.
Madeline, does it matter which comes first as far as the variables like x and y? So like if I put 30x, y, 5, x, 9?
Basically, no, it doesn't matter because with multiplication, we can switch the order. However, the convention is to put the letters in alphabetical order. So it's not wrong to put y first here, but it's normal to put x and then y.
All right, just small question. Thank you.
Yeah, no, it's a good question. It would matter like in the parentheses for f of xy, we do need to have those in that order, but in the actual function, the multiplying, we can move it around.
Okay.
So we're just gonna do one example of a chain rule. I know you've all been wondering when we were going to get to the chain rule. So our regular notation of chain rule with our exterior, interior, and derivatives of each of those is not going to work super well here, but we can still sort of think of the same method. So here our function is e to the x squared plus y. So this is a chain rule because we have our exterior function and our interior. Oops, and see, that's it already doesn't work. Actually, I'm going to leave that as an x because we are doing the derivative with respect to x. So y is not technically a variable right now. So if we have our exterior and our interior, this is really e to that interior function. And our interior would be that whole x squared plus y. You do not have to write this exterior and interior format, but if it helps, then that's good. So I'm just going to use prime notation just to keep up with what the chain rule that we were using, that we have been using all term. So if we're doing the derivative of e to a power, we're still doing the derivative with respect to whatever that power is. So e to a power is just e to that same power. So nothing is changing there. And if we do the derivative of the interior, we are focusing on x here.
So just 2x.
Just 2x, exactly. Because that y goes away. So technically the way I wrote this with the primes is not good math grammar, but if you want to keep with the E exterior and interior format, we can do that as long as you're remembering here we are doing dz dx, so x is really the only variable we're focusing on. Okay. Dx. So chain rule is the derivative of the exterior, so that will be e x squared plus y times the derivative of the interior, which is just 2x.
Can we write it 2xe to the x squared plus y?
Yeah, that's better. It's technically not wrong, but it looks nicer to put the 2x in front. So all that happened here is our regular old chain rule. It's just when we were doing the derivative of that interior, we did the partial derivative with respect to just x. So if we're doing the other partial derivative, dz dy, most of what we just did still applies. So our exterior, I'm going to write this as I of y now because that's the variable we're focusing on. Our exterior is the e with its exponent. Our interior is that exponent. So the derivative of the exterior is still just that same e to its exponent. So really the only thing that actually changes here is the derivative of the interior.
X squared. And that's it.
It would be 1.
1, exactly. So if we're doing the partial derivative of x squared plus y with respect to y, that x squared goes away because it doesn't have a y on it. So that's just a constant.
Oh, and it's not being multiplied. Gotcha.
Right, exactly. If it was x squared times y, we would have an x squared, but it's not. So it's just a 1. So our dz dy in this case is our exterior, or excuse me, our derivative of our exterior, which is just the function we started with, times the derivative of the interior, which is just 1. So we don't actually need that.
That was a lot of work to go back to where you started.
Yeah. So we're almost all of our partial derivatives are going to be polynomials. Most of them, at least. You will have like a few chain rules in your homework, but for the most part, the partial derivatives we'll be working with will be just polynomial type things where we're really just using the power rule. So we're not going to go super in depth into doing these derivatives, but we will be using them for the next couple sections. Okay. So one last little bit of this partial derivative section. Just as a little preview, in section 7.3, we are going to be doing optimization in multiple variables, which means finding maximums and minimums and those kinds of things, the kind of thing that we did in one variable functions. And when we were doing those things, we also talked about second derivatives throughout chapter 4. So we're not going to talk about like concavity and those types of things for multi-variable functions, but we could, but we won't in this class. But we do need second derivatives here as well. So we call them second order partial derivatives. So our notation gets even more fun for second order partial derivatives. This, I'm just gonna make a note of all of these notations are on page 438 of the book. So if you don't want to write them all down, you can reference that.
Will this be something that's on the final exam?
Yes.
Okay.
So if we have just one variable in our, which we've had up until now, when we do a derivative, there's just one way to do that derivative, and then we do the second derivative, there's only one way to do that. So there's really no confusion about what kind of derivative we're doing. But when we have more than one variable, we have to be specifying which variable we're taking the derivative of. And so if we're doing two derivatives, a second derivative, we have to specify which variable we're doing the derivative of both times, which is why there are 4 different notations written here, or 4 different lines here, each with 4 notations. Because if we do x and then x, that's different from x and then y, which is different from y and then x and y and y. So there's 4 possible combinations of the different variables. And if we added another variable like z, we would need to have 6, 9.
So if you're doing a second derivative of x and y, wouldn't it be like an xxyy? Or is that what the xy is?
That's what the xy is.
Okay.
So yeah, so let's look at these. I'm going to start with the first and last ones because those are the most straightforward notations. This first one, f with 2 little x's under it, means we're doing the partial derivative with respect to x twice. So just like we do second derivatives in other functions, we're just doing the derivative once and then doing it again. And here we're doing x both times. So we can represent that by just doing 2 x's on the bottom. The dx notation gets a little confusing when we are doing second order partial derivatives. But if we look on the bottom here, so the little x squared is representing we're doing the x twice. So that means do the derivative of x 2 times. On top, the square is on the d. And we did see that a little bit when we were doing second derivatives before, but we were mostly using the prime notation. So if we have an x squared in the denominator, or this last notation we won't really use that much, but if there's just 2 x's on the bottom, that's saying take the derivative with respect to x both times. And the same thing goes for if we have a yy on the bottom. y squared. So in each of those cases, if we're doing the same variable both times, there's no real confusion about what we're doing. It will tell us exactly what variable to do twice. The notation for the other two is confusing because it's the two notations with the F and the subscripts and the D whatever they don't match. So by that I mean, on this F notation, the X is closest to the F, which means do X first. So we're doing the derivative with respect to X first, and then the derivative with respect to Y. When we write it in the dx, dy notation, it's the variable that it's sort of like the inside variable that looks like it's coming second, but that actually means first. So here we're doing X first. So this line here is do X first. Gosh, I really can't spell first today. First. Then Y. So this, underneath that, the third line here, has the Y closest to the F in this first notation with the F's. And the Y is sort of our inside thing here. So this means to do Y first.
Is that supposed to be X or F?
X, thank you.
Oh, come on.
No, I lost my pen. So that is the confusing thing about this notation. So when we are doing one variable and then the other, the way it's written is a little bit confusing because it's in different order for the F notation and the D notation. So that's mostly practice and just getting used to those notations. So let's practice these. So here is our function. So we really need to do these in separate steps, just like when we were doing second derivatives with one variable, we had to find the first derivative first and then do the second derivative. So we're not gonna like automatically get this right away. So we will start by identifying which variable goes first. And that is the last one when it comes to this D notation. So we would start by finding dz dy. So the partial derivative with respect to y.
So x minus 2.
X minus 2, exactly. So that first term is xy. So y is just 1 of itself. So when we do the derivative, we're left with just its coefficient, which is x in this case. And then minus 2y, the same thing. The coefficient is just 2. So now we are going to do d dx to that. So this is going to end up being second order partial derivative of z with respect to x and y. So we already found the partial with respect to y. So now we are going on to the x. So we need the partial derivative with respect to x.
Would be y.
So we don't have a y here anymore.
Oh, gotcha. In that equation. Okay.
Mm. So each of our partial derivatives are sort of working, they're going in steps. So we started with our function z, and then we first did the partial derivative with respect to y. And so now that x minus 2 is what we are working from to now do the partial derivative with respect to x. So we have x minus 2. What is the derivative with respect to x of that?
1.
1, exactly. Derivative of x is 1, and that minus 2 goes away. For how complex this d squared z over d dx dy looks, we just have a 1. And that happens a lot with second order partial derivatives because we're paring them down quite a bit with each step of the derivative. So don't be alarmed if you do a second order partial derivative and you end up with a cute little answer like this.
So how is that? How is this information like useful or even used in business calculus?
So this is, so let's back up a little bit. So our partial derivatives, if we're just doing first order, are any time we use a derivative in the last few months, partial derivative is how we do that with multiple variables. So for example, if we're trying to find the marginal cost for a multivariable function, we would do the partial derivative with respect to whatever variable we're focusing on. So if we want to know the marginal cost of the standard kayak, that would be the partial derivative with respect to x. And now we can see that that is true because we would be left with just 90 there. Partial derivative with respect to y would be 120. And we can do that with revenue or profit or whatever we are looking at. Second order partial derivative. So in chapter 4, we used second order derivatives or second derivatives to do like the point of diminishing returns, look for concavity, inflection points, things like that. So all of that kind of thing has an analog in multiple variables. So if we're doing second order partial derivatives, that's that same kind of thing. We would be looking for the rate of change of the rate of change. And it is a little bit different in multiple variables because like in this case, we're doing the derivative with respect to y first. So that would be the rate of change of the function with respect to y. Whereas if we do the partial derivative again, now that's the rate of change with respect to y with respect to x. So it gets a little convoluted when we are in multiple variables, but any time we used a derivative or a second derivative in previous chapters, all of that is still applying to multiple variables, which we need in most situations. There are actually not very many real world situations that only have one variable in them. So having all of that information applied to multiple variables is what it's useful for. And so we are going to see how we use next Tuesday. We are going to do section 7.3, which will be about maximizing and minimizing. So we can find out like how to find a maximum profit if we have a multivariable function. And we actually need second order partial derivatives in order to do that. So we will be using these for that. Let me see what I had down here. Let's just do one more for today. So this one, B, we're doing the partial derivative with respect to x twice. So since we have an x squared in the denominator, that just means we're doing an x both times. So we would start the same way by finding dz dx first.
Which is just y.
Just y, exactly. Since the y, or this first term is the only one with an x in it, just xy. The coefficient of x is y, so that's what we have left. And the minus 2y plus 3 is all just constants when we are focusing on y. Exactly. So if we do the partial derivative with respect to x again, so now we're starting with the y that we just got.
So it's just y.
Doing the
Oh,
derivative.
just 0.
Yes, exactly. Since we are doing with respect to x this time, y is just a constant, so that goes away, and we're left with just 0. So test is on Thursday. There is going to be a short homework due on Tuesday about these partial derivatives, and then we'll continue in chapter 7 on Tuesday after the test. So have a great couple of days, and I'll see you on Thursday.
Thank you, Madeline. Have a great day.
You too.
Bye-bye.